小鹏，你把背景换一换。
Go.
Okay, so shall we?
Yeah.
Yeah, okay. So we're 49 groups, and we're gonna presenting our 49 recovery prediction project. And our group members are Changtao, Huazhong, Ziwan Peng, Ricky Tang, Yixin Wang, Hao Chenju, and Yan Jiaxu. Can you move on to the next one, please? So for this presentation, we have the first one, introduction, and then we're going to do SVM and model specification, and how we build the data set, and how we define the falling knives events, and how do we see the samples. And then we're going to introduce what the criteria we used for the impact factor selection. And then we move on to how we can optimize our model and how we can develop it into future use. And the last one will be the UI demo. The next one, please. Okay, so our strategy is not a common ground strategy that can be applied by any investors in the market. So relying on 40 knives events to make profits is actually another strategy. However, in the security, it is the art of the unique thinking that can make huge profits. So no matter it is a mutual fund manager or a hedge fund manager, they all use strategies different from other investors in the market. So whenever investor believe the bull market will continue, they are already shorting them, just as our strategies is doing. So like we're thinking differently from other investors so that we can make huge profits. And investing the 40 knife is actually a type of contrarian investing strategy. So which is one of the most common strategy used nowadays is the momentum investing strategy. So basically, momentum investing strategy is widely used in many large mutual funds or exchange traded funds. However, when most investors are using the same strategy, they can only realize a market return based on the efficient market hypothesis. So this dominant hypothesis states that every single new information will be incorporated into the security price immediately after its release. So it won't allow any investors any time to speculating on it. In order to realize an excess return, we must select the right strategy. So in our model, the strategy is essential, and we must think differently from others. And at the same time, the risk will also be high if we carry out such strategy without careful thinking. Therefore, our project is just doing the thing now to help really to eliminate the underlying risk of such investing strategy. Okay, move on to the next one, please. Okay, so we must build a robust and reliable model to precisely catch the 40 knives, which require computation over tens of thousands of historical data, and we must rely on machine learning to achieve that. Can you move on to the next one, please? Yeah, okay, so as we can see, this is a typical 40 knife. So if an inexperienced investor want to do the contrarian investing, he will possibly buy in during the plummet of the false support, and subsequently he will panic because the price is still dropping, and he had to close his positions and realize huge losses. However, with our model, we can help them to determine if a recovery will happen in the future, and to help them to realize profits for him. Okay, move back. No, move back. I haven't finished. Yeah, all right, thank you. Okay, so as long as we have a robust or solid model, we can get a reliable support for the rebound, which guarantees profits in the future. So considering the stochastic and intricate property of the stock price movements, we cannot make accurate predictions on the stock price, but we are capable for predicting if the upward movement will happen or not in the future. So therefore, we are using the binary classification model to predict if the recovery of a stock will happen in the future. Okay, next please.
Okay. As Hao-Chung mentioned before, predicting continuous stock price is extremely difficult. It's almost impossible to say by how many percent a stock will rebound after a sharp fall. Hence, we need to make the objective more feasible. So we focus on a classification rather than a regression, because regression is on continuous value. Bucketing method separates the price change into two categories. If the stock recovers, the response variable is 1. Otherwise, the response variable is 0. Please move forward. Why we choose SVM as our model? Because SVM is relatively robust on financial data. We know financial data has low signal noise ratio. And SVM is able to deal with linearly inseparable data set. Sometimes it's not feasible to obtain a linear boundary in this case using linear kernel, but we are able to use non-linear kernel SVM. Also, SVM can derive the probability that a stock recovers. And investor can put those stocks with relatively high probability of rebounding into the portfolio based on the forecast. Please move forward. What is SVM? SVM is an optimization. In SVM, we use margin to denote the distance from the boundary to samples. The margin of a certain data set can be denoted as twice the minimum distance from points closest to the boundary And here is a 3-dimension nonlinear kernel SVM. It's a visualization using the first 3 factors of our dataset created by RStudio. And we can see red points refers to those companies recover. In fact, here, red points in the picture, you can see it. And black points refer to those companies fail to recover. The gray boundary is created by the SVM chained on our chainlink dataset. Our chainlink dataset provides a chained SVM model, and we can use this chained model to predict the samples in testing set and validating set, and even the real data set in practical investing. Okay, here is the SVM specification. And then why we use soft margin and kernel? Because perfect separation could be infeasible. For SVM that allows presence of misclassifications, we include a slack variable to measure the misclassification. The parameter C, which is a penalty on slack variable, provides a soft margin. In addition, dataset could be linearly inseparable. Kernel is used to map the data to high dimension where the dataset is linearly separable. And this is what SVM can do. Okay, it's my part.
So next step is the dataset collecting. In order to be able to train our model, we first need stock historical data on the US stock market to help us determine whether the stock has fallen nice or whether it has finally recovered to the price. So in order to, for our trained model be universal in a certain industry, we choose to obtain the longest possible historic daily data of all stocks. In order to achieve this, we first need to know the stock codes of all United States stocks. So through searching, we found that almost all US stock codes are collected on this website, as shown on the slide. We then use crawler technology to organize them into a local table for future use. And there are a total of 15,096 stocks. The picture on the left is the name and code displayed on the website. And the picture on the right is a screenshot of Excel after recording it. Next. So next, we need to find a website with historical stock data. And we finally found those data on the Yahoo Finance website. And we can download the corresponding CSV file according to the data and the stock code we selected. So we wrote a Python software based on the enter the stock code and the date, provided it to the Yahoo Finance website, and let the server of Yahoo Finance to return us the corresponding data. Due to the corresponding time required, in order to download from the website more efficiently, we packaged this Python code into an exe tool and wrote in the introductions for other users. And the picture on the right is the introduction we wrote. Next. And this page is a display of a specific step to use. So after unzipping the toolkit, there are 3 files. One is the description. The other is the Excel file with several stock codes, and the other one is the main program. After running the main program, it will download the corresponding daily data according to the stock code in the stock code file in the same folder, and finally generate a stock code table that failed to download. After the program runs, the data file name in the folder is the stock code, and inside the file is the historical price data. So next page. And in addition to stock price data, the analysis of different industry requires different factors. So we discuss the corresponding factor data according to the actual analysis need. And all company-related factor sources and the macro factors come from 2 different websites as shown in the slides. And we use a similar method discussed earlier to obtain different data in different industries. And the picture on the right shows part of the factor data. Next. And because of the large amount of data, we first distribute the developed tool to all team members. After that, the required data is divided into blocks, and each person is responsible for one piece. And finally, we assemble all data together and complete all data collection. And now our data is temporarily stored in the Google Drive in the form of CSV files, which is convenient for us to use data on a small scale. And afterward, if we want to use the MapReduce by Spark for large-scale model training in the future, we can easily convert all Excel file into an Oracle database in the future for us to use. So that is the database part.
Yeah, and to train the model, we need to define 49s and filter real 49 events samples from our database, just built it. To complete this step, we developed an automatic script which can help us to detect the 49 events. The UI of this script is shown in the image here. Once we input the falling days we define and the average falling rate, the script will find the data which follows the definition automatically and copy them out. And it will give a label 1 to the stock which recovers and give a label 0 to the stocks which not recover. The left-hand side of the image is the first phase of our definition. In the very beginning of this definition, we tried to set falling knife as events that a stock lose 30% of its price in one day. However, when we set a script that depends on this definition, the sample we got are highly concentrated in 2008 and 2020, just as the image above. It means that we failed to detect the normal falling knife events that did not occur in financial crisis. However, this part of events are extremely important. As we all know, the government usually gives the loose currency policy in financial crisis. Therefore, if we just use the events happen in financial crisis, it may lead to high survival bias. It will extremely affect the performance of the model and increase the prediction error dramatically. After discussion, we realized that the definition we made are too restrict, so that the events we detected are can just happen in systematic financial crisis. What we need to do is to relax the time period of fall and narrow down the daily falling percentage in order to simulate a normal falling knife. Actually, we need the falling knife events in our sample are uniformly distributed on the timeline from 1986 to 2020. At the same time, the density of the falling knife every year should be appropriate to the reality. After several times of attempt, we decided to define the falling knife events as here. We relaxed the falling period from 1 day to 3 days and narrowed down the average falling percentage from 30% per day to 10% per day. After this adjustment, the sample base we got become much more normal. The distribution of our final version of sample set is shown in this image. As the image, we can see the amount of falling knife events for each year are almost the same. And because of the financial crisis, the amount of 2008 and 2020 is a little bit higher than other years. By this distribution, we can see that the definition we use at this moment is the one we can explain the falling knife normally, and we will use this definition in the rest of our project. This is my part.
Okay, the next part is about the factor selection. The most two things we consider are statistical significance and the correlation. To select factors, we use the multi-factor model. It's a financial modeling strategy in which multiple factors are used to analyze and explain prices. More factors means higher complexity in parameter optimization. So in this process, we would like to use the least number of factors that can satisfy the information required. Next page, please. In total, we have 4 steps: candidate factor choosing, validity testing, redundancy factor eliminating, and factor adjusting. At the first step, we select some candidate factors that have different frequency from the 3 aspects: macroeconomics, the market, the complaint characteristics. For each of the 3 aspects, I will take one example to explain the reason why we choose them. First, for the macro, the TED spread is an important macro factor, which is the difference between the 3-month T-bill rate and the 3-month LIBOR. It reflects perceived economic risk, monetary liquidity, and perceived credit risk of the global financial banking system. And the return and the trading value of S&P 500 are used as the proxy of the market return and the market activeness in the second aspect. And at the complaint individual level, we assess from profit scale by its size, debt level, creditworthiness, volatility, concentration, and valuation. For example, the ROE and the ROA directly reflect a company's profit scaled by its size, so they are selected to stand for its profitability. And next. Okay, the second and the third step are validity testing and redundancy factor eliminating. We use the sequence modeling, t-test, and the p-value to assess the validity of candidate factors and only keep the effective and unique factors. But some of them are highly correlated with each other because they are driven by the similar intrinsic elements. To deal with this problem, we set 0.8 as the threshold for those factors whose correlation coefficient is greater than 0.8, we only keep the one that has lower correlation with other factors. And the final step is adjusting. We need to adjust the factors according to the model performance. When we do the data drilling, we have the overfitting issues that requires us to add more impact factors. And Zivan will introduce the overfitting issues in the next chapter. And please, next page. And this picture shows the final factors we use. It's 19 factors. Okay.
Well, after we finished all the preparations, we split the dataset randomly into training data and test data as 80% and 20%. Then we start to train SVM model. So here is our result. We use confusion matrix to evaluate the model's performance. You can see from the picture, the true positive and the true negative are correct, which means that the model predicts that this stock will recover or fall, and this stock does recover or fall. False positive means the model predicts that the stock will recover, but in fact, stock fails to recover. False negative means that the situation that the model predicts the stock will not recover, but in fact, it recovers. And the ratio of total number of true positive and true negative to full training data is the accuracy rate. We can see from the matrix, in training data, the accuracy rate is about 86%. In test data, the accuracy rate is 77%. So we can see this result is not good enough. So there may be two issues. First, actually, in real business settings, false positive weighs more than false negative because false positive may cause loss, increasing the portfolio risk, and false negative cause less of loss because the user just misses a potential opportunity rather than suffer a loss. And the second is the overfitting issues, the most common issues in machine learning. That is to say, our model perform well in training data, but perform poor in test data. Next slide, please. And so, based on these two issues, we needed to optimize our model. For the cost-sensitive issue, we applied weighted linear SVM. And for the overfitting issue, we applied bagging and imposed more impact factors. Next slide, please. So, as for the cost-sensitive issue, in our initial SVM model, which you can see from the left one, the penalty C, the soft margin in the objective function, is the same to the false positive and the false negative. So, based on cost-sensitive considerations, we needed to adjust the objective function, imposing different penalty as C1 and C2. You can see from the right picture. Since false positive weighs more than false negative, we needed to set bigger C1 than C2. Next slide, please. And as for the overfitting issues, we applied bagging and a large data set, which are the most sufficient ways to avoid overfitting issues. Bagging is to adjust the hyperparameters so that the model won't capture unnecessary features and produce less variance. Basically, it's like bootstrap samples and spread their weights evenly to produce the final model hyperparameters. And larger data set means that we need more firm-level impact factors to capture the important features of price changes. Then, next step, please. Then, after we run the corresponding packages in RStudio to adjust the model, the final result is very good, actually. We can see from the confusion matrix. In training data, the accuracy is 92%, rose by 66%. In test data, the accuracy is 94%, it rose by 15%. It's huge. And the false positive decreased to 4 and 0, which shows that our weighted linear SVM did a great job in cost-sensitive issues. Therefore, we solved these two issues and got the final prediction model with excellent performance. So we move on to the next step. Now let Tianjia introduce the UI demo for us.
Okay, so after model developing and optimization, the next step is to design a user interface. The UI focuses on anticipating what users might need to do and ensuring that the interface has elements easy to access, understand, and facilitate those actions, providing a link between the algorithm solver, the stock database, and the user interface. A potential user will be able to obtain the prediction of most recent foreign knives on the user interface based on the uploaded data. Actually, we use Shining to create the user interface. It's a package that makes it easy to build interactive web apps straight from R. Okay, please move on to next page. Okay, so you can see the image on the right shows how the interface looks. The output includes the data import, threshold, a factor import, and a summary of the model prediction on the bottom. So with the user interface, users can upload their own recent stock data on the left side and choose the macro factor, market factor, and the individual factor from the database. As a result, users can predict the recovery of foreign knives based on the factors they prefer. They can also set the threshold, which represents the growth rate of stock price. Only when a stock whose price increases above the threshold can be considered as a recovery. So the default threshold level, as you see, is 20%, but users can set it by themselves, depends on their risk tolerance. So for those risk-averse investors who prioritize the safety of principal over the possibility of a higher return on their money, they can choose a higher value as the threshold. With a higher threshold, the model will become more rigorous since the number of foreign knives decreases. To some extent, this will improve the accuracy of the prediction, but will lose some foreign knives that will recover. But for those investors who won't take the risk to get the profits, they can choose a lower threshold on the growth rate of stock price, seeking more investment opportunities, actually. Okay, this is my part. Please move on to next page.
Okay, so so in the entire process of improving the model, we tried many different methods to eliminate issues like overfitting and false predictions, and we all managed to achieve that. But like it's inevitable to mention that in the future, if there are any needs to expand this database to the level of hundreds of thousands of data, the SVM model may not be the ideal one because it is unable to handle that huge volumes of data. So like, sorry. So at that time, we need to reconsider the model, and it takes money, takes human labor to expand our database as well. At this current stage, SVM model works perfectly fine, and the results given to us are reliable, robust, and promising. So this is already a big success for our project. So like we have to consider if this is a product in the future, like we're gonna require more funds, more human labor, and of course the computing powers. Next one, please. Yeah, that's it. All right. Thank you.
No. Thank you. Can you rate? So I think this was very good. Let's I guess the next step is let's take a look at the model itself. But I will stop the presentation right now.